Good morning again. This is part two of section 4.7 optimization problem solutions. Again, I'll get it to a certain point where I think you can then either take the derivative yourself and find the max, the min, or whatever else might answer the question, or you can grab the calculator and let it help you find the max or min and then again answer the question. The two problems I'm going to look at are 33 and also number 37. 33 is one of the more challenging ones. But basically what we have is this situation. Our goal is to minimize the surface area of this three-dimensional figure. And basically it's like a capsule where you have a cylinder and then on two ends you have a hemisphere. Now when you have a hemisphere on each end, you put it together, you have a sphere. So if we want to minimize the surface area, in other words, we have a certain volume, a certain amount that we want to contain inside this capsule, but we want to use the least amount of material to create the capsule. So if I start with that, minimize surface area, what I need to do is come up with a formula for surface area. And you can either look in text or just listen to me right now. But basically the surface area is going to be the surface area of the cylinder. And the cylinder would be 2 pi r h. 2 pi r would be the circumference of the base of the cylinder times the height, plus the surface area of the sphere. Surface area of a sphere is 4 pi r squared. So you look at that, you think, great, I've got my what I call primary equation. I have to find the derivative, set it equal to 0, and do all of our max-min theory. However, we see an r and an h. I don't want that. Now, we do want to find the r that creates the minimum surface area, so I want to get rid of the h. And this is where a secondary equation comes into play. We are told that the volume of this thing is 14, I believe. Let me check that. Yes, the volume of this thing is 14 cubic units. So the secondary equation would be 14 is going to equal the volume of the cylinder, which is pi r squared h, plus the volume of the sphere, which is 4/3 pi r cubed. So what we now need to do is take this expression and solve for h. And this is where it does, as I said, it gets complicated. But we solve for h. We know we can subtract 4/3 pi r cubed from both sides. So we got 14 minus 4/3 pi r cubed. Then I would have to divide by pi r squared. Again, that's quite a complicated expression for h. So what I'll do is simplify it a little bit. I'm going to split it up into two separate fractions. I got 14 over pi r squared and minus 4/3. This pi would cancel along with two of these r's. So hopefully that looks a little bit better. So now my primary equation is area is 2 pi r h, and that's where I get h. So 2 pi r, h is this whole expression, 14 over pi r squared minus 4/3 r plus 4 pi r squared. Now, we'll go a little bit further in trying to simplify this. That'll help you out some. Distribute the 2 pi r. This is going to be 28. The pi's would cancel. The r's would cancel and leave one r in the denominator. So that came out rather nicely. The next part, we'd get 8 over 3. You're going to get an r squared, but you'd also have a pi. So the final thing to do is maybe recognize that these two terms are like terms because they have the pi r squared. So we can go one step further to write 28 over r. Now if we take a 4 And in negative 8/3, what would that be? Well, this is going to be 12/3, so it seems to me we get 4/3. We then find the derivative, and this is one I will find the derivative for you. Remembering r is your variable, it's going to be negative 28 over r squared. The derivative here would be 8/3 pi times r. Now we can set that equal to 0. We can find the r that makes it happen. Of course, we could have stopped at this version of the area, graphed it in the calculator, and found the maximum. But many times I do want to show you the one calculus step. So now we could use our calculator to set that equal to 0 or do it by hand. So that's going to be problem number 33. As I said, the complicated part were some of these geometric formulas and realizing that the primary equation of what we want to maximize or minimize was surface area. So I started with surface area and I worked to getting that to be only in terms of r. The other problem is to maximize the strength. Well, one thing I've said is that whenever we have a word that comes after maximize or minimize, we want a formula for it. We don't know a formula for strength, so we're given a formula. And the formula was given as K h squared W. So the strength of this beam of wood is K h squared W. K is just a constant of proportionality because it has something to do with how strong the beam is going to be based on its dimensions. So that's a constant. We don't have to worry about that in differentiation or any type of the calculations. Again, we have two variables. We don't want it. But then we notice our cross-section picture in the text is that we have a 20-inch diameter log. And what we'd like to do with that is basically create a beam. So this little picture lends to our secondary equation of W squared equals H squared. How about this? 20 squared equals H squared plus W squared. Now you might think you need to solve for H or W, but if we look back at the original, there is an H squared in that formula. So I'm just going to solve for H squared. So I get H squared to be 400, which is 20 squared minus W squared. So now my strength formula is S equals K, again, just a constant, H squared, which is 400 minus W squared, times W. So my strength formula would be K times 400W minus W cubed. We then find the derivative, set it equal to 0, and we get the width that will lead us to the strongest beam. Once we have the width, we can find the height. Remember to always go back and get the answer in terms of what you're looking for, whether it is the height, the width, or in this case, both dimensions. Well, I hope that helps for a few of these problems. Throughout this week, as you're working on anything from 4.7, 4.8, or even the worksheet that I posted, please send a message by email or any other way. And if there's a collection of those by the middle or end of the week, I can have another series of these short videos to give you some guidance in how to get through these problems. Hang in there. Hopefully we'll see you soon, and have a good Monday.